As far as performing a test goes, we are still using a test statistic, a t-score, like before. We're looking at something like the distance from a mean of a sample to a mean of a population divided by a standard error term, where in this case the mean of sample is really a difference of means, as is the mean of the population, where it's important to understand that when we're taking these kinds of tests, because there's always at least included somewhere in the null hypothesis that the two population means are equal, this term we generally take it to be 0. Not least of which also because we don't technically know what these things are, and it just makes our lives a little bit easier. So really we're going to be looking at a difference between sample means divided by a standard error. But for our t-test with independent means, we have two varieties that we deal with. Either we have pooled or not pooled, where the language of pooled versus not pooled can also be talked about in terms of variances, but in either case, what that really determines for us is behavior for the standard error term as well as the degrees of freedom. It changes a little bit here. For the pooled case, essentially what we're assuming is that our two populations are, at least in some sense, very similar, if not the same. So similar that we can take their variances as equal. So when we're looking at this stuff, if you either see something that refers to the populations as having equal variances or pooled samples, pooled populations, those mean the same thing. And regardless of how it's referred to, when we're looking at something like that, what we have to bear in mind is a term called the pooled estimate for the standard deviation. That is the pooled estimate of the population standard deviation, which is denoted with a sigma hat and is a really nasty term that you can see right there. The square root of n1 minus 1 times s1 squared plus n1 minus 1 times s2 squared all over n1 plus n2 minus 2. Where in that case, we end up with the standard error having the behavior s x1 minus x2 is equal to that pooled estimate sigma hat times the square root of 1 over n1 plus 1 over n2, and we have degrees of freedom equaling n1 plus n2 minus 2. So if you see that the sigmas are equal or pooled, then you know that that's the process you have to follow, which is kind of a nasty one that I never expect you to do by hand. There will not be a context in which I'm going to ask you to do that computation. It's simply not worth your time. You've got better things to do. You've got more tests to run than it's worth it for me to see you compute those square roots. Don't worry about it. If it comes up, let the calculator do most of the work, which I'll talk about in a second. But it's also not really a very fair assumption in my eyes to say that the two populations are similar in that way if we're assuming we don't know that much about them to begin with. So more reasonably, if we want to deal with the non-pooled sample or the samples where the variances are not equal, then in that case we have a slightly different behavior for the standard error, slightly different degrees of freedom, where for that we have that s x1 minus x2. I'm thinking those should be x1 bar, x2 bar, whatever. But for those, we have the standard error is equal to the square root of s1 squared over n1 plus s2 squared over n2. It's nice to deal with, but I still don't really care if you do that by hand. And degrees of freedom given by the smaller of the two sample sizes, minus 1. Where we take the smaller one because when we're dealing with the t-distribution, remember it's always sort of an approximation to the normal, and we always want to leave the most room for error we can when we're making an approximate. So we pick the smaller one, means we're taking a little bit more weight into those tails, we're leaving in a little bit more space just in case things went wrong with how we grab stuff. So we always take the little guy where we can. If they're the same, it doesn't really matter. But we'll see what that looks like with some examples. Anyway, as I said, it's a lot of work doing this kind of thing by hand, and it's only going to get worse from here on out. And 8.3 is, well, it can be quite a mess, and so is the test that we'll see in 9.1. So I really don't expect you to do this by hand. Don't expect yourself to do this by hand. Get comfortable using the two-sample t-test function in the calculator or whatever other computational method it is that you happen to prefer. Stick with that instead. It's much more efficient. In any case, when we're dealing with these, we have the same type of testing procedure as before, where if we want to use p-values, we check that the conditions are met to work. In this case, that's that the sigmas are unknown and that the central limit theorem holds for both of our samples. Then, run your hypotheses and claim, specify what alpha is, find the test statistic and the degrees of freedom, being careful about whether the samples are pooled, Then, get your z-score, space, and the p-value that goes with it, make your decision and interpret your results. On the other hand, if you want to deal with this using the critical value rejection region approach, you would verify that the conditions are satisfied, just like before, state the hypotheses and the claim, just like before, level of significance, just like before. Then you find your degrees of freedom, get your critical values, rejection regions, then get your test statistic t-score, make your decision, and interpret the results. Just like before, though. Process follows the same kind of steps. The math in between is a little bit different. Your hypotheses look a tiny bit different. And when we get the distributions, you'll see they're not quite exactly the same. But in terms of how the pieces work together, in terms of how we set things up, in terms of how we make our final decisions, it actually does follow very much the same patterns. Where again, I prefer the p-value method for exactly the same reasons I did in Chapter 7, but we'll try and see a little bit of both here, just to understand how this all works, starting with an example.